Greetings everyone. Good morning, evening, or afternoon. So we are from Group 1, from Group Fabrication of Nanocomposite Material using Plasma Enhanced Chemical Vapor Deposition. So our group consists of myself, Krisna Ramadhani Fauzan,
dan Muhammad Rufna Hanifah.
And Fatima Zahra Maulidia.
And Dian Maulidi Hanif.
So on this presentation, we're gonna present about 5 points, which is the backgrounds of its fabrication of PECVD, its basic principle, methodology and result, application, and its the conclusion.
Okay, for the background, next, Mas. For the background in this journal is the first one is hard coatings are essentials in tribological applications due to their low frictions, wear resistance, thermal stability, and oxidation resistance. Plasma-enhanced chemical vapor depositions enables precise control of microstructures, making it a preferred method for synthesizing advanced coatings. And while coatings like titanium nitride, titanium carbon, and titanium carbonitride demonstrate excellent mechanical and tribological properties, their plastic deformation resistance remains a limitation. Traditional superlative structures struggle with thickness and uniformity, especially on three-dimensional objects. Existing nanocomposites also require optimizations to achieve a balance between hardness and elasticity. In previous studies, nanocomposite coatings synthesized via PECVD have achieved hardness of 45 GPa and Young's modulus of 350 GPa. However, integrating carbon into the silica carbonitride matrix to enhance properties remains underexplored. A promising candidate, TIC-NY-SICN, could potentially offer superior mechanical performance. This study synthesized titanium carbonitride and silica carbonitride nanocomposites using PECVD with controlled precursor gas mixture methane. The goal is to develop coatings with optimized hardness, wear resistance, and elastic properties. Research objectives are to synthesize and characterize the microstructure and mechanical properties of titanium carbonitride and silica carbonitride coatings to evaluate tribological performance, including frictions and wear, against existing titanium nitride and silica nitride coatings to determine the optimal carbon concentration for enhanced material performance. Next. For the basic principle, plasma reactor is based on the utilizations of plasma as a medium for chemical reactions. Plasma consists of positive ions, free electrons, and highly reactive neutral molecules, which can accelerate chemical reaction or facilitate material depositions. Next. The first one is the system is set to low pressure using vacuum pump in order to eliminate atmospheric gases that could interfere with plasma reactions. The next one is pressure gas such as nitrogen, ammonia, methane, or ethane are chosen based on the material intended to be synthesized. For the plasma formation, a DC voltage is applied to the electrode to generate plasma between the anode and cathode. Accelerate electrons within the electric field collide with gas molecules, leading to ionizations and the formations of reactive radicals. Next. In plasma reaction, ammonia produces active nitrogen radicals and hydrogen radicals, which are crucial for forming nitride layers. Methane or acetylene decompose into active carbon, facilitating the creation of carbon-based layer. Nitrogen gas is typically used to create an inert atmosphere or to act as an additional nitrogen source for the reactions. The substrate is placed on top of the cathode and is typically heating using a heater. Active radicals react with the substrate, leading to the formations of the desired material layer. Next.
So the next one is methodology for this journal, which is the quaternary hard composite, titanium carbonitrate and silicon carbonitrate coatings prepared by plasma enhanced chemical vapor deposition. So So on the schematic of the PICD, this journal used the version 310, which have a radio frequency of 15.56 megahertz. So the systematically, the purpose of this journal is to find the thin film, which is have the most used for its hardness and stiffness. So there will be some measurement and also using this transmission electron microscopy tools, which is XRD, XPS, and also ERD. So moving towards the process, so this film deposition, firstly, have to have the system was pumped down to 1.333 millipascal using a turbomolecular pump backed by a rotary pump. So this proposes to provide clean environment. So next, after it cleaned down, the inside of the chamber is flat space for the substrate and can be heated called the platen, and the high resistivity crystalline silicon, which is using the 100 wafers, were used as the substrate. And then the next one is the source gas flow into the chamber with this material, which is TiCl, titanium tetrachloride, nitrogen, and also silicon hydro with the different concentration of the CH4, which is the methane. So there will be six samples, which have the difference of standard cubic centimeter per minute. And also next one, the high voltage of the RF, which is the radio frequency, is applied to the chamber, which create the plasma and ionize the gas molecules. So this ionization process make the source gas chemically reacted. So after that, this reacted molecule form a thin layer on the substrate with have the growth rate of the film is constant with a desired thickness can be achieved by running the process. So from this process, the thickness of this journal is ranged between 2.7 until 3.3 micrometer. So this also the process have a 6.66 pressure Pascal, and also there is 3 hours main deposition process. And to stop the thin film disposition, we turn off the RF voltage and stop the gas flow. And when the film gas disposition is complete, we pump the chamber down again to remove the gases and the byproduct. So from this methodology, there is three measurement tools that is used to analyze the film disposition. So there is the XPS, there is also the XRD. So XPS is the X-ray photoelectron spectroscopy. So this aiming to see the surfaces composition of the chemical composition of the microstructure. And also for the SRD is aiming for the crystallization structure, which were carried out by the Philips expert refractometer. And also the data collected in this journal is 0.5 degrees to enhance the surface sensitivity. And next one is the transmission electron microscopy, which is TEM. So this is to analyze the visualization of the microstructure and the nanoscale and offering a high resolution image to access structural integrity, morphology, and uniformity of the films. So for the results of this, so for the XPS and also the ERD TOF, which is the time of flight. So the results is the first sets of experiment will perform a detailed study of the chemical composition. Here we can see that from the table one with increasing of the CH4 from 6 samples, we can see that the C or the carbon is increasing, which replacing the R at the end, which is the nitrogen. So if the carbon is increased, it will replace the nitrogen. So the nitrogen will be decreasing. We can see from the sample 1 and sample 6 that the carbon is increasing from 0% concentration bulk to 22.9%, while the nitrogen is 38.6% to 18%. And also this measurement indicates similar levels of surface of contamination due to C and O. And for the table figure 2, figure 1 of the ERDDOF, we can see that it has similar data to the XPS, which from the sample 1, there is no concentration of C. And from the samples 3, we can see that increasing the sample, there is the presence of the carbon, but the nitrogen is decreasing. So the XPS table and the ERD table was completely the same, but therefore we assume that there is a 7% contamination because uh, that the XPS spectra due to the adventitious carbon. So we value the C by subtracting to the carbon concentration with to the film bulk. So next one is the chemical composition and microstructure. Here is the XPS. So we can see here there is a lot of peak with there is four, which is the Si2P, SC1S, titanium 2P, and also nitrogen 1S. So this for figure which indicates the peak will have a different binding energy range. So for example, for sample titanium 2P, we can see that mostly from 1, 3, and 6, the titanium presents with the same binding energy. But from the sample SIN, SEO, and SITI, we can see that the presence of the CIC and CITI creates another peak, which decreases the SIN. So the SIN peak is getting lower, while the SIC, SITI is getting higher. So now the results is analyzed using the XRD and TEM. So here we can see the diffraction angle and also the intensity. So from sample 1, 3, and 6 is indicating that the increasing of CH4 flow introduced that the carbon into the TIN structure results to the progressive transition from TIN to titanium carbonitrate. So with a reduction of crystalline size at higher carbon content. While in the TAM analysis, we can see that there is two sample uses, which is the sample 1 and sample 3. We can see from these findings that the carbon incorporation, which is the CBUG at 9.1%, result in the formation of mixed titanium carbonitrate without disrupting the overall crystallinity of the film. So here we can see that the structure is more complex than in sample 1, uh, that it shows a shift peak in position, which indicate that carbon atom replace some nitrogen atom in the TIN crystalline lattice. So for the result is the mechanical property. So this the purpose of this journal is to have the most best scorings for the film disposition. So here we can see that from the figure 5 is the load displacement curve. So this graph shows how different corings behave when force is applied to them during the nano indentation test. So a test to measure hardness and stiffness by pressing into the material. So here we can see that the titanium carbon nitrate and silicon carbon nitrate have the highest hardness and also Young modulus, which is 57 GPa and 306 GPa compared to other courings. And next one is the figure 6, which is the hardness also as function of carbon content. Here we can see that the best of the concentration of C is at 10%. So we can see that in 10% there is the most highest hardness and also the most best Young modulus. And the next one is in figure 7. So this graph shows how well the coring is resistant to plastic deformation and permanent damage when force is applied. So here we can see that the most scattered data is the best one. So here we can see the square, black square. It means that titanium carbonate and silicon carbonate have the best results, which is it has the most scattered ratio than the others shapes.
So the next one is the application of DICX-MI or CICN coatings using PCPD. So this coating produced by PCPD are used by in wide range of application due to their superior mechanical properties and stability. Tribological application, DICX and Y coatings with their hardness and wear resistance are often used in cutting tools, wear resistant surface and mechanical components subject to high stress and wear. High temperature coatings, both material coatings exhibit excellent thermal stability and are used in high temperature application, such as turbine blades, heat shields, and exhaust system in aerospace and automotive industries. Electronics and semiconductor devices, CICN coatings are also utilized in the electronics industry for the protection of microelectronic components and semiconductors, providing protective barriers against oxidation and improving device longevity. Next. Okay, in the case of TICX and Y coatings, PCPD is used to deposit titanium carbonitrate films which have excellent hardness, wear resistance, and corrosion resistance. The resulting film possesses a combination of titanium and carbonitrate bonding that imparts mechanical strength, high thermal stability, and good electrical conductivity. By adjusting the ratio of the precursor gases and the plasma powers, the properties of the film, including its hardness, refractive index, and chemical composition, can be tailored for specific application. CICN film are known for their excellent thermal stability, high hardness, and chemical inertness, making them ideal for high-performance coatings. Particularly in aerospace and microelectronics, the stoichiometry of CICN can be adjusted by varying the flow rates of the precursor gases. The resulting films can have various ratios of CI, C, and N, affecting their properties such as mechanical strength, resistance to oxidation, and wear resistance. By tuning parameters such as substrate temperature, plasma power, and gas flow rates, PSPD allows for precise control over the composition and microstructure of SiCN.
Of the titanium carbonate or silicon carbonate films were deposited using FPECVD under ion bombardment. As for the structure, the nanocomposite films are embedded in a silicon carbonate, which are 5 to 10 nanometers in matrix. For it also consists of the phase segregation, which is suppressed at less than more than 15% with silicone to titanium bonds forming. For the mechanical properties section, the hardness levels are 55 GPa at minus 9.1% for peak performance, and it drops to 25 to 30 at GPa at more than 15%. For the H3 or ER2 as plastic deformation resistance, 1.8 GPa versus 0.8 GPa for the titanium carbon nitride or silicon carbonitride is 1.3. For the Young modulus value, it's 302 GPa. The elastic rebound is around 80% high. The toughness are 0.1 MPa, and for the compressive stress is around 2 GPa. And last but not least, the friction wear, which consists of coefficient of friction, which is 0.13 times 10 to the power of minus 6. And for the wear rate, it's 12 times 10 to the power of minus 6. And before we end it, this is a reference page for the journal that we use in order to create this presentation.
So that's all from us from fabrication of nanocomposite using PCVD. Thank you for your attention. Wassalamualaikum warahmatullahi wabarakatuh.